Assalamualaikum warahmatullahi wabarakatuh. Pada kesempatan kali ini kita akan membahas mengenai hukum ampere. Hukum ampere digunakan untuk menentukan besarnya medan magnet di sekitar kawat berarus listrik. Adapun yang akan kita bahas adalah mengenai formula hukum ampere dan aplikasi hukum ampere pada kawat lurus sangat panjang yang berarus listrik, silinder sangat panjang yang berarus listrik juga, kemudian pada solenoida dan toroida ideal yang berarus listrik.
Out of the page, it's coming out at us. So I'm going to just draw the cross section of the wire, and it's got a current I going through there. Oh wait, the current's going to go into the page. I drew an X, so the current's actually heading into the page. And so now, if I want to know the field, say right here, what I do is the field is actually circulating around, and the field right here is down. Using my right hand rule, I found that. Let's see. Yeah, it curls this way. Put my thumb in the direction, my right hand, thumb in the direction, it curls like that. So it's I'm going to draw an Amperian loop. Now this isn't a sphere, this is actually a loop. And that should have been a circle. It's a pretty bad circle, I understand. And so I'm going to just write down Ampere's law. U naught I through the Amperian loop is equal to the closed loop integral of B dot dl. And then I'm going to, the first thing I'm going to do is I'm going to say how much current is going through the Amperian loop. Well, all of it is. All this I is going through the Amperian loop. So I'm just going to say mu naught times I. I'm done with that side. And that's equal to, now I'm going to get rid of the dot product because for every point on here, B is this way, B is this way, B is this way, B is this way. The DLs are always parallel to them. These little DLs make up the Gaussian loop. So these little DLs, they're these infinitesimally small DLs, they make up the Amperian loop. So I'm going to get rid of the dot product because B is parallel to DL at every point on the Amperian loop. And then I'm going to argue that why would B be stronger here than here than here? Because of the symmetry, they're the exact same strength. And so I can pull that B out of the integral. And so when I do, I'm just left with summing up all the DLs. Now, if I sum up all these DLs, then do you see that I just get 2 pi r? And so you can bring the 2 pi r on the other side. So let's say I have a current this time, the wire's coming, the current's actually coming out, so that means that the field is going to go this way. So if I want to know the B right here, that's what I'm after, the actual strength of the B right there, then I'm going to draw an Amperian loop. I'll be a little more careful with this Amperian loop. It's got a radius r, and I just apply Ampere's law. Mu naught I is equal to mu naught I is equal to the integral of B dot dl. Now I'm going to say that the total I coming out of there is just capital I. So this will just turn into mu naught times I. That's how much current is going through the Amperian membrane. And that's equal to, now I'm going to make the argument, since the field is this way, B is upward this time. Right here, B is this way. Right here, B is this way. Right here, B is that way. And so since B and DL, we'll always pick DL to be in the same direction as the B. See how they're parallel at every point along the way? dl is this little vector, and I don't mean to have it curve. It's actually a straight vector, but because it's so little, they make up that loop. And so I'm going to get rid of the dot product, because B is parallel to DL at all points on the Amperian loop. AL is Amperian loop. And then since I'm going to make the argument that since you're at the same location at each one of these points, it's the same distance r away from the wire, then I'm going to make the argument that B shouldn't be any different at each point on here as far as magnitude goes, not direction, but magnitude. And so that's why we need symmetry. Without symmetry, we can't make that argument. But because it's symmetric, I can. And so mu naught times I is equal to, I'm going to pull that B out. And now I'm summing up all the DLs. This is saying sum up all the DLs. Oops, we got rid of the vector. And when we're summing up all the DLs, this is actually a definite integral. It's saying start at some point and don't stop summing them until you get all the way around the entire loop. This is no longer an area. This is actually a loop that you're going around. And so when you do that, then you're going, well, let me give you this argument. This argument, why I was able to do that, is that B is uniform at all points on the Amperian loop. And then when I add up all those DLs, then I get that it's B times 2 pi r. Okay, let's bring the 2 pi r on the other side. And so if I were to graph this, what is B? How does B vary with r? If I were to graph this, it looks like it does one of these. It's like a 1 over x graph. Okay? That if you just put two wires next to one another, they don't cancel. So here's one wire, here's another wire, and even though, you know, the current could be going this way here and this way here, you might think that out here these two currents would cancel each other, but they won't, because if you think about it, the field from this guy right here is going into the page, so I'm going to put a little X from there. Actually, I'm going to put a big strong X from there because it's really close. Whereas the current from this guy is up, and so that's going to be a weaker field, and so those don't cancel because this current is just further away. I've drawn this so it looks like it's twice as far away, and so let's just say it is. Let's say that the distance between these two is d, and then this is another d out all the way out to there. Well, the field from this guy is going to be mu naught I over 2 pi d, whereas the field from the further wire is going to be mu naught I all over 2 pi, if they have the same current. I'm assuming they have the same current. 2 pi times 2d. So it's half. This is half the field. And so they're not going to cancel out. Whereas if they're along the same axis, let's say we have a cross-sectional, a circular cross-section of wire. Let's say the wire's coming like this out of the paper and into the paper. And let's make some dots here to show this is current. The current is actually coming out like this. And let's say it's uniformly distributed. So in fact, let's talk about the amount of current coming out. We'll talk about it in terms of current density. So current density is a known. We'll call it J. Remember, J is equal to I over A. And that's a known. I'm going to have J in my answer. And what I'm going to want to find is the magnetic field, say, in here a distance R away. lowercase r away. And eventually I'm going to also want to know what the field is out here, another distance little r away, we'll say. But let me first find the magnetic field a distance r away, like say right there. And we also have to make one other assumption, and that is that that mu naught is equal to the mu of this material. So this material has its own permeability, and let's say that it's pretty much equal to the permeability of free space. Okay, so if I want to know the magnetic field there, I'm going to draw an Amperian loop, and this Amperian loop is going to be circular. So there it is, distance r away. And so all that matters is the current that is passing through the Amperian membrane. Here's the Amperian membrane. Okay, so I'm going to write down Ampere's law. Mu naught times I through the Amperian loop is equal to the integral, the closed loop integral, the closed path integral, closed loop or closed path integral of B dot dl. And just to remind you, this B is not just any old B, it's the B on the Amperian loop. It's the B right here. And these DLs, these are the DLs that make up the Amperian loop. These are little line segments, DLs. Okay. So, as you might guess, the B right here is going to be, well, let's just talk for a moment about the B that's due to these guys out here. We're going to get a cancellation effect from these because the B's from here are right there. They're going to be putting a field that way, where the B's from here are going to be putting a field this way, and so you're going to get a cancellation effect there. And I'll talk more about why that is a cancellation effect in a later video, but for right now, the only B that's going to matter, according to Ampere's law, is going to be the B that's enclosed, or the I that's enclosed. All the rest of it cancels. Kind of like in Gauss's law, where we said the same thing. And so I'm going to say that starting here, mu naught. Of course, if it's not mu naught, I might have to use whatever the mu is. But I'm going to just call it mu naught for right now because it's equal. The mu in there is equal to mu naught. And then the I through the Amperian loop. So the I is going to be just J times the area, this area. So it's going to be J times this area. So pi times little r squared. You see how that gives me the I through the Amperian loop? That's equal to B dot dl. So now the first thing I'm going to do is I'm going to get rid of the dot product, because you see the B right here, if I use my right hand, it's circulating that way. So the B right here is going this way. That's a B, that's a B, that's the magnetic field direction, But the DLs are also going that way. Just draw a bunch of little DLs. Now, how many DLs are there around here? An infinite amount. Why? Because they're infinitesimally small, each one. But the B and the DL are in the same direction. So we just lost the dot product, because what is the dot product doing? It's taking the part of B that's in the direction of DL and then multiplying it by DL. So how much of B is in the direction of DL each time? Answer, all of it. So, and it does give you a scalar product, so that's why the dot product disappears there. And so that's because the argument for this last step is because B is parallel to DL at each point on the Amperian loop. Okay, then I'm going to argue that you can pull the B out of the integral because of the symmetry of the situation. Why would B be any stronger here than here than here than here? It's so symmetrical that it wouldn't. And so mu naught times J pi r squared is equal to When I pull that out, it's just going to be the sum of all the DLs around the loop. And so the sum of all the DLs around the loop are gonna, when you add them all up, you're just gonna get 2 pi r. Okay, let's get rid of the pi, get rid of one of the r's, and bring the 2 on the other side, and apparently b is equal to mu naught times j times r over 2. Okay, so if I were going to plot that, see what that looked like on a graph. Apparently, if I go out twice as far from the center, these are all constants, I get twice the b. If I go out 3 times as far, I get 3 times the b, all the way out to the edge there. So I'm only going to plot this from 0 to r for right now, because I don't know about outside. But inside, it's linear proportion. B is directly proportional to R. Okay, I want to just finish off this problem then. What about the B outside of this? This is a wire. The current is coming out at us. This is just a cross section of the wire. The wire is coming up, and it's also going into the page. This is, we call this capital R. And what happens if the B is, we want to know it out here, maybe a distance r, lowercase r away again. Okay, we draw a Gaussian, or it's not a Gaussian, an Amperian loop here, circular. Remember that the current density in there is J. So the current density in there is J. And so that's supposed to be a circle with its center here. And so I'm going to write down Ampere's law. Mu naught I is equal to the closed loop integral of B dot dl. Okay, so the B is going to be, the dots are coming out at us, and so the B's are going this way. Draw a few B's. If you want to know the direction of B, it's always, if you draw your radius out there, the B should be perpendicular to that, because this is really a tangent line. That's a tangent vector. So that's B. And here's some DLs. I'll show you some DLs too. DLs aren't curves. They're actually just little segments that are infinitesimally small. Okay, so how much current is going through this Amperian loop? Well, none is going here, is it? It's all on the inside here. So the current that's going through the Amperian loop, it's only going to be mu naught times, now since J is equal to I over A, it's going to be J times A, but I only want this area. So that's going to be pi times big R squared times J. So it's J times the area. That gives you the I. This is the I. And then that's equal to the closed loop integral of B dot dl. Now we'll get rid of the dot product because B and dl are always in the same direction. So this is the argument. B and dl are in the same direction at all points on the Amperian loop. And then I can pull the B out of the integral, because why would B be stronger here than here than here? Because of the symmetry. So mu naught times J times pi R squared is equal to B times the closed loop integral of dl. This is just now saying add up all the dl's. And I can do that because B is uniform at all points on the Amperian loop. And then when I do add up all the dl's, I'm just going to get two pi times little r, because that's the Amperian loop. So I can get rid of a pi, but I can't cancel out those r's anymore. And so it looks like B is equal to mu naught J r squared, which is just a constant. R squared is just a constant. Divided by 2r. And so if I'm going to go and finish this graph, it looks like it's going to be equal to, since this is all this other stuff is just constants, it looks like it's a 1 over r graph, which behaves like that. It swooshes down, something like that.